Noah Akers, and this is my um, Physics 2 Lab 5. Oops. Okay. Oops. So my overview. So the goal of the lab was to analyze the interactions between a falling magnet and a tube of aluminum foil. And Faraday's law is used to relate the bar magnet's magnetic field to the induced current within the aluminum tube. And with the computational model, I've found that the magnet falls in the tube for 0.65, and for the experimental, you see that it falls for 0.55. For the procedure, I just marked the north pole of the magnet and recorded 5 trials and determined how long the magnet was falling through. So as you can see, this is all the experimental data, as well as the average time for the magnet, which was 0.55. So here's some key concepts. Faraday's law: the flux is area times the magnetic field, and the derivative of the flux is equal to the EMF, and voltage equals IR. And yeah, you can use this within this and relate it to each other. So this is the computations I made. I'm sorry if it's cut off a little bit. Um, but yeah, sorry, this is for the computational model, and this is the code. Yeah, you can pause the video and take a look at that. But this is the outputted graph. Yeah, you can't see, it's kind of cut out, but on the top it says velocity versus time. Well, you can see that. Yeah. Um, but yeah, as you can see, the time in the tube is 0.65 seconds, and yeah. So for the conclusion, what if the magnet was flipped around? Well, that would make the magnetic flux increase upwards. So the induced current would just change directions, or change to the opposite direction. How does my real world system compare to the computational system? Well, in the real world, there's other things like air resistance. That's like actually pretty big thing that could affect your real world experiment, which is why our data was different from the 0.55 that I observed to the 0.65 that the computer computed. And yeah, thank you.